In this exercise, we will cover mass average velocity, molar average velocities, and volume average velocities, which can be included as mass flux and mass velocities, molar fluxes or mole velocities, and so on. And before we even continue, I just want to remind you that this is just a refresher of fluxes, velocities, and flows. If you want to get more technical on this side, you should go and check out a transport phenomena course or a mass transfer course, which is based on diffusion. Okay, for now, I just want to show you these to refresh what is the main difference between these species. So here we go. A gas mixture containing 65% ammonia, 8% nitrogen gas, 24% of hydrogen gas, and 3% argon is flowing through a pipe of 25 millimeters in diameter at a total pressure of 4 atmospheres. Okay, first things first, we are not given any kind of value of the percentage. So you could be talking about mass value, molar value, or volumetric values. Since we are talking about gases, I'm going to assume that this is molar value, even though it's not for sure, but let's say for the sake of this example that this is true. And it's flowing at a diameter of 25 millimeters. So I'm going to assume that this is the internal diameter at the given pressure. The velocities of the components are as follows. And this is not typical, guys. You will not see, or you will not encounter this in real life, but this is for the sake of this exercise. Typically, what you will find is a total velocity of all the gas, not of the individual materials. But anyways, as you can imagine, hydrogen gas, which is the smallest one, will be the fastest one. And the slowest one will be argon or nitrogen. That's interesting. So maybe it's also because of the percentage. I don't know. For now, just ensure that the range goes from 0.02 all the way to 0.035. And the topic is estimation of mass average velocity, molar average velocity, and volume average velocities. Okay, so essentially mass velocity, molar velocities, and volumetric velocity. And it goes respectively as mass, find the mass or calculate the mass average velocity, molar average velocity, and volume average velocity. First things first, let's go for mass. And as you can imagine, we will need to use molecular weight because we want to change these values, which we are assuming as moles, to the mass value. From the formal definition of the average velocity, here we go. So first we gotta find the individual densities times the individual velocities, add them up, and divide it by the total density of the components or the mixture. And if I wanted to do the separation, we will get 1, 2, 3, and 4, which is 1, 2, 3, and 4, respectively. And I'm using T because that's how the nomenclature comes, but typically we will use ρ. And T is the total density, as you can imagine. So, here we go. We can calculate the total density, which will be here, as the total pressure divided by the ideal gas constant, divided by the temperature of the system, times the total molecular weight of all the components. So this is an average as well. Talking about the average, we need to calculate it. So here we go. The total molecular weight is, or the molecular weight of any component given moles is the molar fraction times the individual molecular weight. Here we go, 1, 2, 3, and 4. We know it's 65 for ammonia, 8 for nitrogen gas, 24 for hydrogen, and 0.03 for argon. And the molecular weights, 17, 28, 2, and 40. Performing the calculation, we get something around 15, which can be grams per gram mole or kilo per kilomoles. And now that we have this value, we can go back to this part right here and substitute the values. So that's what I'm going to do. We got the molecular weight, the velocity of reported velocity, and its molecular weight. So this is molecular weight, molecular weight, molecular weight, and molecular weight. And this is the total addition. Probably you're wondering why, because we're talking about this one right here. And then what I'm going to do is solve for the total average velocity of mass. So I just need to divide by the total or average molecular weight, which is something around 15, which is this data. And I get this value. I know it's a little bit messy, but what we are getting is an average. As stated before, we got something between 0.20 and 0.35. And this is in between, which is great, 0.029. That's for the mass value. We need to calculate the molar value, and this is more interesting because we don't need to get messy with molecular weights. We are given directly the molar compositions and so on. Now, instead of densities, we're going to be using concentration, and you know that the concentration can be calculated as the pressure divided by RT. And then if I perform the calculation, you can see that we get the individual vapor fraction or composition in the gas phase. So this is gas phase. Do not confuse with this Y value, even though it's the same, but for now, assume these are different because these, we're talking about direct comparison with the molecular weight, the moles, sorry, this was molecular weight. And what I'm going to do is essentially just substitute. And as you can see, this part right here is pretty similar to this one right here, but we don't have to add the molecular weights. Why? Because we're not talking about mass. And now that we have this one right here, this will be the total molar velocity. And probably you're wondering, why do we have different values? Because we are talking about moles that are moving per meter second, and in the previous case we're talking about grams that are moving per meter second. And C is the most interesting part right here, since we are going to assume, or we already assume, ideal gas is valid. Then remember that we can relate the volume velocity as the same as the molar velocity, which is this one right here. Meaning that if we're talking about cubic meter or centimeter, that will be the velocity of the area. Which, if you were to calculate the pipe and you have the area, you will see that this is the actual volumetric flow rate.